one this way, and then up one. And then if you connect those together, you get your tetrahedron like that. Is that all right? That is definitely a solid. Let's look at its shadow on the ground. Be real careful here. Notice what your x and y are, right? Because remember, red was x, right? This was y. So here, that's not drawn to scale, but over one, up one, something like that. And then here, like that, right? Should be that. Now look, isn't this a type 1 region? Isn't this type 1? Like, aren't your x's between two constants? Right? What's this constant here? 1? Aren't your x's between two constants? And are y's between two functions of x? Absolutely, I agree this is type 1. But you can also look at it as type 2. You can look at it either way with this one. I'm going to do type 2 intentionally so you can see the difference. So our y goes from 0 to 1, right? Our y goes from 0 to 1. I'm looking at this as like a type 2. Our y goes from 0 to 1. Our x's are between these two things, right? But remember, when you define this curve right here, it needs to be solved for what variable? Y or x. Hold on. We want it to be a function of y, don't we? So, well, what is the equation of that line? Y equals x, right? But we want to solve this for x, which it already is solved for x. It's a little confusing. But remember, when we're doing our restrictions on x, right? Y is between two constants. Our x's are between what? What's this? 0. And what's this? Y, not x, right? Y. Yeah. And now you need what? One more thing. Restriction on z. And z comes from the tetrahedron over here. The bottom surface, right, is z equals 0. And the top surface is, shit. What's the top surface?
Do we have to use the points to find the plane?
Yeah. Yeah. So we need the equation of the plane, don't we? But I didn't give you the plane this time. I just gave you the points. So how do you find the equation of a plane? If you have 3 points, do we have 3 points on the plane? Make sure you have the right ones. This one, and this one, right? You have 3 points on the plane. How do you find the equation of a plane if you're given 3 points?
Oh, you remember if you have a vector and a point on the plane?
Yeah, okay, close.
So you could sort of make a vector?
We can create a vector going from here to here,
Yeah.
and create a vector going from here to here. And once we get those, we have to create the vectors, remember? Create them. They're not the points. You have to create the vectors. Then once you create the vectors,
You do the
cross product,
get the normal.
that'll give you a normal, and then all you need is a point. You actually have 3 of them. You can use any of them.
Yeah.
Yeah?
Normal vector.
Once you get that equation, what do? Solve for z, and then you have your surface. Do y'all want to go through all that work, or do you want to do it? Okay. You could use the refreshing? I thought that would be just right on the tip of your, no? Okay. So let's get the points. The points are 0, 0, 0. This one was, careful, this one was, I think, 0, 1, 1. Yep, 1. And this one right here was 1, 1, 1, 0. Make sure you get the right points, because shit, if you include that point right there, you're going to get basically z equals 0. You're going to get the friggin' ground. You don't want that. All right, let's find these vectors. I'll call this v1, and I'll call this one v2 so we don't confuse them. All right, so v1, remember, before we get too far ahead, Remember, this is all we're trying to find, right? Is that upper limit of integration. Remember all this stuff because I'll need it. So V1 is the vector that goes from 0, 0 to that point, which is 0, 1, 1. That's a vector. And then I have V2, which is the vector going from there to here, which is just that written as a vector as well. And now to get the normal vector of that plane, what I do is I take the cross product of these two, right? Yeah. So I cross these two, and so I'm going to get good old-fashioned cross product. We cover this up, then we do the little blah, 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 blah. So what do we get?
0
minus 1. Okay, and then we cover up the middle one, and we make this answer negative. Cover up the middle one, cover up the middle one. It's 0, and then minus 1, but then that's a negative in front of it, right? And then lastly, cover up that one, 0 minus negative 1. Oh, why did I put a parenthesis? Sorry, vector. Negative 1, 1, negative 1? So negative 1, 1, negative 1. That's our normal vector. All I need is a point now. Hey, how about the origin? 0, 0, 0. Okay, so to come up with the equation of plane, what we do is we use a normal vector, negative 1, parenthesis, x minus the x coordinate, 0, plus the next number here, 1, then y minus 0, and then plus, actually it's going to be minus, won't it? Because minus 1 there, so I'll make it minus 1, and then z minus nothing. I didn't have to put the zeros, I'm just so you can go back and look at it. So we get negative x plus y minus z equals 0. And then solve for z, so move the z over to the other side. And then z is negative x plus y. And that is going to be the surface right here, negative x plus y. That's it. Now we set up the triple integral, right? Now we set up the triple integral. So we're supposed to do the triple integral over e of x, z. So now my triple, I'm looking at my limits. I've erased them. But the y was between the constants, right? It was between 0 and 1. Then my x was, don't tell me. Yeah, 0 and y, right? 0 and y? And then my z we just got here was 0 to negative x plus y. And then we're integrating xz d z d x d y. Restrictions on y, on x, on z. Okay. What do you think is coming next? The shadow was type 1. Well, the shadow was a box. Got it. The shadow was type 1. Got it. Shadow was type 2. Got it. Shadow's polar. Right? That's where we're going, right? We will go there. Hold on. Let's see exactly what's on the notes, but you can kind of start to see where this is headed. And if we go to polar, don't we have to put an R in there and stuff, and things are going to get weird? Okay.
Yeah.
All right. Whoa. That's the way you feel sometimes, right? Impaled by the x-axis. X-axis? Yeah, it was x. No, that was that? No, that was x. Oh, it was y. It was y? Yeah. Felt like x. Triple integral over the region E. All right, consider more possibilities. So we're not going to do this. We just need to know just how bad this could be, right? Because when we have this solid here, right? When we have this solid here, we're talking about a shadow on the xy plane, right? Being a box or rectangle or type 1 or type 2, right? But there's nothing stopping us Like what if your surface, or what if your solid doesn't have a top surface and bottom surface this way? What if it's not a function that way? What if it's only a function this way? Like you have a surface on this side and a surface on this side, and the shadow you're looking at is on here instead of on the ground. Then the shadow over there could be a box, or it could be a type 1 or a type 2, right? Or over there, cast a shadow on this plane. You could have box, type 1, type 2. It can start to get messy. So this is basically me saying all that. I'm saying, look, what if your shadow on the ground, but you're looking now, look at the ground. The ground is now the y what? Z plane. So you're looking at y, z. Your shadow over here is a type 1. So your y's between two constants, your z's between two functions of y, and now your x is between two surfaces, right? Your x is between two surfaces. Where's the second one? I don't know where the second one is. Where'd it go? Where's U2? I think U2 is up too high. Where is it? I don't know. Well, the important thing is that this surface on the bottom is a function of y and z, not x and y. And then surface here. We're not going to do these, all right? It's just so we know that there are these other possibilities.
Thank you.
Yep. Now, I do have a problem in here where I have us do, I believe that's the same problem we just did, right? I believe it is.
Yeah.
Where we do that tetrahedron that we just did, looking at the shadow on the xy plane. That's what we just did. But then I say, let's do the same problem, but then now let's cast the shadow on the xz plane instead. And you wind up getting the same answer. We're not going to do it, right? I won't test you on that. Is this class long? Does this seem like a long class to you?
No.
You all right? So I said this was coming, right? Polar seems like the natural next progression here. Evaluate the triple integral over E of Z with respect to volume, where E is the solid bounded by the cylinders y squared plus z squared equals 9. Interesting. Yeah, it's a sideways one. All right. I'm giving you a chance to just think about that for a minute. We have to figure out what E is first, right? And the reason we need to know what E is because E is going to allow us to get our limits of integration, right? What are our restrictions on X? What are our restrictions on Y? What are our restrictions on Z? Shit.
Is this one where we have to orientate ourselves to the plane to get the shadow?
Yeah, I think we're going to have to go a different shadow. That's why I'm wondering if I really want to go through this. Let's just do it. Let's just go through it, okay? I mean, it's an example I normally do in this class. I don't want to stray from that. Let's just see what happens. Let's see if we can at least get what E looks like. Can we do that?
Yeah.
So we have a cylinder, right? Y squared plus Z squared is 9. That goes down the x-axis. Radius of 3, right? Got the cylinder going down this way. Now, drawing this is going to be an absolute disaster, but I'm going to go for it. I have a cylinder going that way. There's my cylinder, okay? X equals 0. This is the x-axis. This is the y. This is the z. X is 0. What's that? That's the back side, right? So it was going this way, right? And it's x is 0 is this. So it's kind of like cutting it. That means I have a back side of this circle, don't I? I can kind of do that. Not good. Not good. I'm sure that we could get 3D software to do this for us, but let's keep going. Z equals, we got that. Z equals 0 is what? The ground, which means it's cutting that in half, right? So now it looks more like this, here, 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 here. Are y'all seeing that? I'm going to redraw it. We still have the other side. That's right. Yeah, no, I can't cut that off yet. It comes around the other side. Yeah. Oh, Jesus. Okay, it looks like this. It looks something like that. That's still bad. But we're not done. We're not done. We have y equals 3x. What is that? It's a line, right? Cutting through. So here's y, here's x, right? Y equals 3x is a line that kind of cuts through like this, like that. And remember, it's a plane, isn't it? It's a plane. So it pinches off this thing. What does this thing look like?
Like a pie?
Like a little bundt cake slice almost, right? And you all know what a bundt cake is?
Yeah.
Yeah. This is hard to see. This is hard to see. Let me try and zoom it in a little bit. So let's start with we've got that blue piece coming like this, that, right? And then it goes like that. And it goes on the other side as well, right? Like that, and then continues out that way like that. This thing curves over. But we're cutting it off on the bottom, and then we have this line that comes through. And the plane that comes through. When that plane comes through down here, it cuts it. And so what we get is something that looks like this. Something like that. So, yeah. I didn't want to, I actually could have drawn this a lot, like right off the bat, but it's important to see, like, you have to develop it, right? Like you have to say, okay, it's this and that, and then this is cutting, then you know what, maybe start over, right? If I just would have been like, hey everyone, that's just like this little like slice of this thing, right? That's sitting, like, no, right? We have to try and see if we can develop the picture. Okay. What kind of solid is this? That's our solid, right? That's E. I think we can do this. I think we can do this with the shadow on the ground. What's the shadow on the ground? It's a triangle, type 1, right? And then you have a top surface and a bottom surface, right? The top surface is just part of the cylinder, isn't it? Okay. So if I take that cylinder, I would have to write it as a function of x and y, which means I just solve for z. So I have a square root in there, but I should be able to handle it. So I think we're in business. Now, I definitely would recommend that you would try this, use Desmos 3D or GeoGebra to kind of help you graph this, right? If you're having trouble with it. Domain. Let's talk about this domain on the ground. Don't forget what everything is. That's x, that's y, right? That's z. So my domain on the ground, here's x, here's y. It looks very similar to what it was before, right? It was like that, goes over, this thing keeps going up. That's y equals 3x. This is our d. Yeah? So hold on. What is this? What is this? Because remember, we're trying to do a type 1 here. We're going to try and get our x's between two constants, our y's between two constants. Do we know this from here to here? What is that on this picture over here?
3.
It's 3. Why is it 3? It's the radius of the cylinder. It's the radius of the cylinder. So this is 3. And I think with that knowledge, you can actually figure out what this is now. What does x have to be?
1.
1, right? Because that's 3x, remember? So if I plug 1 in, I get 3. Yeah? Yes?
On the final exam, are you going to have a question where it involves us having to pick some sort of image like this?
It'll be much more complicated.
Oh.
Yeah, no, it'll be much more difficult than this.
Okay.
No, I think, no. I don't think so.
Okay.
Yeah. All right, I think we can do type 1 here. But your homework will definitely involve things like this.
Okay.
Definitely. All right, so x is between 0 and 1, right? Or y is between two functions of x. Yep, so this one, lower. 3x, that's this. Upper one is 3. And we may as well now get z. Z is, all right, so let's get our surface from E. The bottom is 0, right? The bottom is the ground. The bottom is the ground. And the top is this curved piece, which we take that equation, solve for z. We get square root 9 minus y squared. Remember when we solve for z, it'll be plus or minus. But because we're looking at the top part of this, it will only be the plus. There it is. Now we set up the triple integral. The triple integral will be, let's see, 0 to 1, 3x to 3, 0 to, ew. Now I'm thinking I might have to plug that in at some point. I sure hope, well, this will be what I plug in for z, right? So I'm really hoping that when I integrate, I'm going to get a z squared, which I will. Just so happens to be. Now dz, dy, dx, because again, those are the limits respectively. Yeah. So you go 1/2 z squared is your antiderivative here, and then you plug in that for z, it squares and it goes, square root goes away. So it turns out to be not as bad as it may look, but we're just here to set things up at this point, right? We are not grinding these things out, right? 10 minutes, let's just see where we are here. So these are the cast shadows, more of it. Oh, okay, here we go. Wow. So now that we have this idea of a triple integral, right, we can go and extend on what we started class with, which was the idea of mass, center of mass, moments of inertia. But now our solid, we have instead of a lamina, we just have a solid sitting in space. And that solid has a density function, rho of x, y, z. And using the same sort of idea, but this time using the definition, the true definition of density, which is mass over volume instead of mass over area, we can get that this is area, this is volume. Excuse me. This is our density, I should say. This is our density. This is our volume. Density times volume gives you mass. And so we're summing up all the little mass points. That gives us our total mass. And then we have moments. But when we have moments, in this case, when we're in three-dimensional space, we don't have just the x and y axis. Right? We have the z-axis as well. So we have the moment about planes. Moment about the plane. The yz plane is this, so we add an x in here. Moment about the xz plane, we put a y in here. Around the xy plane is z. And so you can calculate those. Question?
Is the order of the letters of the moments matter, like that, when the partials are relate? Like you see when you...
These aren't partials.
No, I know, but
Okay.
I'm just asking, because if you're not to the partial derivatives, is that order?
This order doesn't matter. It just means that, I mean, normally we would say the yz plane, but you could also say the zy plane.
Okay.
I mean, it means the same thing. The important thing is that if you're trying to find the moment, where's the yz plane? Here's the yz plane, right? You got this mass sitting out here. Here's the YZ plane. The distance to that object is x. So that's what's being put into the integral. It's what variable is missing, exactly. So the moment about the xz plane, you want to measure distance y and include it in there. So you got your 3 moments, right? Now, to get your x bar, y bar, z bar, you're going to do the moment about the yz plane over the mass. To find the y bar, you do the moment about the xz plane over the mass. Z bar, moment about the xy plane over the mass. So how many integrals do you have to do? How many triple integrals do you have to do to find the center of mass of something?
4.
4. You need the mass, then you need the 3 moments. Then you have moments of inertia. But you have the moment of inertia about the x-axis, the y-axis, and then about the z-axis. And here's the formulas for them. We're not going to really do anything with this. It's just to show you. Now, theoretically, if you have a solid that has a non-homogeneous density, that means the density is varying throughout the solid, you can still find the center of mass. You can still find its moments of inertia. Now, in a physics class, you don't go through all the triple integrals. What you do in a physics class is they say, hey, we've got a ball, right? And the ball has a calculated, well, center of mass of a ball is pretty easy, but that's if it's homogeneous, right? If it's not homogeneous, it's a little different. But they'll just give you a formula. They won't do all this. They'll just give you like some end result. And so you don't wind up in physics doing these triple integrals, but you wonder where these formulas come from. They come from like this computation. All right, I feel like I'm missing something. Hold on. There's something here. Where is it? There. I knew it was in here. Super important. This is going to end the day for us. So remember this. This was really important. I asked you to put a star next to it. Double integral of 1 dA. When we were doing double integrals, if you do a double integral over the region D of 1 dA, what did that give us? The area of A, right? The area of A. I'm sorry, the area of D. The area of D. Well, similarly, if you do the triple integral over E of 1 dV, then you're going to get the volume of E. Yes?
So when we were dealing with double integrals, we had a special property
Mhm.
where we could split the integrals between each other if the functions did not have next one.
Great,
Could you do the same
great question.
rule?
Yes, you can. It doesn't come up very often, but you could.
Okay.
Yeah, good question. Let me just recap this. I still have 5 minutes, but I'll only take 1 minute if you allow me. Maybe. So this idea right here, I want to show it to you in every case that we've seen from Cal 2 to now. If we do the integral of 1 dx versus double integral of 1 dA versus triple integral of 1 dV, right? For this, I have to signify what I'm integrating over. I put E, and everyone understands that's the solid we're integrating over, right? And this gives you the volume of E, right? Here, I have to give you what we're integrating over, D. So here's my solid E, right, in 3-dimensional space. There's my E. Here's my D that lives in 2-dimensional space, right? This gives me the area of D, right? And then over here, do we put something on the bottom? No, we write what? A to B. Isn't that what we do? But really, you could say instead of A to B, you could just call this, I don't know, let's call it I or something like that. And what's I look like? Some interval, right? That's why I used I. It goes from what, A to B? Yes? And so what would this be equal to? The length of the interval I. That's what it is. If you integrate 1 from A to B, your answer is B minus A, which is the length of the interval. So do you see how, I mean, this is kind of cool, right? It works like with each dimension, this is a special case, right? This special case right here, if you have 1 here back in Cal 2, it's just how long the interval you're integrating over is. Because that interval is one-dimensional. One-dimensional has length. Here, your region's in 2-dimensional space. If you integrate 1, you get the area of that. Here, 3-dimensional space, you get the volume of that. And this just keeps going. If you had 4 over some, I don't know, let's call it Q because it's weird, and then D, what do you call that? I don't know. H for hypervolume or something like that. This would give you the what? The whatever we call it. Hypervolume of Q. All right. Y'all have a good weekend and everything else. Y'all have a mini exam due on the 6th, right? Which is Monday. Okay, it is Monday. And then this next one is due also on the 6th, right?
15.
Oh, 15. Okay. Sorry. I believe you have everything you need to do this mini exam now. Yeah, because we're done with 12.5, aren't we? Yeah. Yeah, we're done with 12.5, so you need everything. Yes.
There's a piece of cardboard on that board there.
Oh, that's too small.
Oh.
But if you want, y'all can go, but I can go see if I can find a piece of cardboard. It's a fun experiment. Let me see if I can. I found one. I found a pretty good one. I don't have scissors, but what is this going to tear this into something weird? Let me see. Now this won't be perfect, all right? But all right, so this is what I was saying. If you take this and hang it like with a thumbtack or something, if I hang it and drop. Oh, this might be a little bit too big for me to throw. It'll work. Okay, if I hang it, drop a plumb line straight down. That look pretty straight to you? Okay, pick another point. Do the same thing. Draw a straight line down. And I'll do one more for good measure. I don't know, does that look? Let me do one more. That looks pretty damn good. So that's the center of mass. So let's see. First thing I'll do, watch out. First thing I'm going to do is I'm going to throw it into the air just straight up, but I'm going to spin it, and we should just see it go up. The point should just go up and down. Oh, shit. Okay. I might have to throw it through the air. It's folded. Let me throw it through the air. See what happens here. I think I went too ambitious.